Okay, so continuing with the 2000 local exam, we're going to do 11 through 20. So starting with 11, how many milliliters of 8 molar HCl are needed to prepare that much of that concentration? Okay, so here, probably the easiest way to do this is to figure out how many moles are in this particular solution. So that would be 0.15 liters times basically capital M is moles per liters, right? So these would cancel, and then you get left with 0.2 for 240, I guess, in sig figs, moles of HCl. And then you need like a certain amount of volume of 8 molar HCl in order to get that. So it will be 2 point that much, and then X is just going to be my volume is equal to 8. So if we switch these two places in the equation, we can just do 0.24 divided by 8 to get X equals 0.0300 liters, which is the same thing as 30 milliliters. So that's why we get a 12. Okay. Well, easy enough. So basically for these kinds of problems, what you do is you just imagine the percentages are grams. So if you have 21.8 grams of magnesium, you divide by the molar mass. I'll just show the calculations only for this one, because if I do it for all of them, it kind of gets tedious. So we're dealing with magnesium here. And then this gives us 0.897 moles of magnesium. And then if I do the same thing for phosphorus, it should give me, here we go. So 0.894 moles of phosphorus. And you can just consider those the same number, basically, like they're within error. And then 50.3 divided by 16 is 3.14 moles of oxygen. So if I divide 3.14 divided by like any of the previous like 0.89 something numbers, it gives me 3.5. So if I'm in a ratio of 1 to 1 to 3.5, that's the same thing as 2 to 2 to 7. So that means that C is my answer because they're in a 2 to 2 to 7 ratio. Okay, so basically we're just we're combusting ethanol and we just need to balance the combustion reaction. You don't have to use like any weird redox methods for this. If you balance it normally, it'll just balance. So it's per mole of ethanol, so we can just put 1 here, and even if we get fractional stuff afterwards, like that's how we would keep it. So since there's 2 carbons on this side and there's only 1 source of carbons on the right side, we need to multiply by 2 here. And then same thing with H's. There's 6 carbons or 6 H's on this side, and this is the only source of H's, so we need to make sure that there are 6 on this side. Then if we multiply and add up, there's 4 oxygens here, and then there's 3 oxygens here, so 7 total. So, and then 1 contributed by the ethanol, so we need 6 from this O2, so that means we have 3 here. So the question is asking how many moles of gaseous products we formed. So 2 plus 3 is equal to 5. Okay, ammonia is produced in accordance with this equation. Okay, so for percent yield, you just want to take the starting materials. So in this case, 0.5 mole of each reactant, and then react in like ideal conditions to figure out how much you should have produced, and then divide how much you, or divide basically like how much you actually produced by how much you should have produced in order to get the percent yield. So here, H2 is going to be limiting because you need 3 times as much of it more than N2, but obviously since you have the same amount, you don't have enough H2. So that means the amount of NH3 produced is going to be 2/3 times 0.5, which is 2/3 times a half, which is 1/3, right? Yeah. 1/3 mole NH3 is produced or like under ideal conditions. And then that means that 1/3 divided by 1/4 basically. Or hold up. No, my bad. So 1/4 is formed in reality. So we do 1/4 divided by 1/3, which is equal to 3/4, which is equal to 75%. So that's how we get A. Okay, this one looks like you need to know Beer's law, but you really don't. So the important information is that you start with 250, or you start with 20 milliliters, and then you go to 250. So what is that? That's a factor of 12.5, right? you get 12.5 times more dilute or 12.5 times less concentrated. And then the absorbance is 0.15. So hold on, let's draw. So that's about like 0.075 molar, right? But this is the version that is 12.5 times less concentrated. So we need to actually multiply this times 12.5 in order to get the original concentration. So that gets us 0.9375 molar, which is 0.94 basically. And then for 16, you don't really need to know any theory. You can just like reason through it basically. So gases won't behave ideally, or like they'll deviate from ideal when the intermolecular forces are significant. So that can mean two things. If you have a low temperature, that means that the gas particles aren't moving that fast past each other, right? So they have more opportunity to spend near other gas molecules and get affected by them. So that means that we're looking for a low temperature when they're not behaving ideally. So that means a high temperature when they are behaving ideally. So cross out any low temperature answers. And then if we think about the same thing for pressure, if there's a high pressure, then they're close together, they're like bumping together. And once again, there's opportunity for one gas particle to affect another. We don't want that if we want them to behave ideally. So we need a low pressure, not a high pressure. Okay, so this is the same thing as 560 milliliters or 0.560 liters, 273.15 Kelvin. Okay, so it looks like we just find the molar mass of the gas. So we do PV equals nRT, but in this case, we'd be solving for N. So N equals PV over RT. So that would be 1 ATM times 0.56 liters over 0.08206 times, what is RT? 273.15. So that means we get an N equal to 0.025 moles. And then if we do 1.6 grams divided by that, we end up with about 64 grams per mole. And then we're just looking for whichever one of these gases has a molar mass like that, and that's C. Okay, so oxygen is 16 times as dense as hydrogen, so it diffuses. Okay, so you can delete half of the answer choices based on like just logic, right? So if it's 16 times as dense, it's not going to move as fast. So you can't have a number that's greater than 1. And basically the ratio of the speeds is equal to the ratio of the inverse of the molar masses. So like I said, that implies that if you're heavier, you're going to move slower. So it's just 1/16, right? Which is equal to 1/4, like the square root of 1/16. So that's how we get B. Okay, number 19, how is the vapor pressure of a liquid in a closed container affected when you double the amount of the liquid? Okay, so the fact that it mentions the liquid means that there is liquid left over in the container. If there wasn't liquid left over, then the story might have changed because you might have to like vaporize more of the liquid in order to satisfy the vapor pressure, but there's liquid left over. And the vapor pressure of a compound or like of whatever is always going to be the same at a particular temperature. So if you have liquid left over and then you add even more, it's not going to change the vapor pressure. It's going to stay in liquid state. So the vapor pressure is going to stay the same. Okay, a low molar heat of fusion, fusion just means melting, is expected for a solid that is. So a low molar heat of fusion means it's easy to melt. So ionic solids should not be easy to melt. Neither should metallic solids. Neither should network covalent solids. So you're left with molecular. All right, that was 11 through 20. And we'll cover 21 through 30 in the next video.